All right, good morning, everyone. Welcome back to Math 161. Hopefully we've had time to work on some homework. Remember the 1.2 and 1.3 due dates were previously posted. You can find those at the beginning of each lecture or end of each lecture, as well as in my math lab as due dates are generated. I'm about to update the due date for 1.4 in my math lab. I'm actually trying to remember if I did it before class or if I have to do it after I started, and then I think I got busy and I might not have finished, but that's okay. You will see that due date change today, no later than, I don't know, let's just call it noon. It's a blanket, but sooner than that for sure. And that due date will be February 1st because we will finish that section today. We started the section last time. We did an introduction to complex numbers, basically talking about imaginary numbers, which we said is a giant misconception. These numbers do exist. It's just a mathematical concept that's imaginary. We're not going to have that big argument. Why are we dealing with numbers that don't exist? They do exist. So we talked about what the square root of -1, what we're going to call it from now on. We're going to call it I. We're not going to say it doesn't exist, which is wrong. We're not going to say it's not real. That was right, but a blanket statement. We say it's I. And then we showed how we can simplify things like square root of -4, square root of -50, cube root of -27, I squared, etc., etc. Today, we're going to learn how to add, subtract, multiply, and if you saw me in person, I'd be doing air quotes around this, divide complex numbers, because we can't really divide most of them. We have to use a trick that we used for dividing radicals, in fact, if you remember that. But we'll show you what we mean in just a few. And after we finish 1.4, we're going to do a quick, roughly about 40-minute review of factoring. And when I say quick 40-minute review of factoring, I mean quick, like one example of about each type of factoring, and that's it. Remember, we said that you need to brush up on factoring on your own time for this course. It's technically prereq material. I'm not supposed to go over it at all. We're just supposed to jump right into things. But I still like to take about half a class to introduce those topics. And then when we come back next time, we'll really start our journey in 1.5 quadratic equations. All right, so picking up where we left off, we're just going to say that we can add, subtract, multiply complex numbers the same way. And then example 2. Okay, we're going to have 3 plus 5i, and then plus 6 minus 3i. So how do we add complex numbers? The same way we add real numbers, the same way we add numbers and variables, in fact, like terms. That's all it is. So you got, we got these parentheses, so we're going to FOIL things. No, there's a plus sign here. This is not FOILing. This is not that somewhat more complicated process. In fact, these parentheses are completely unnecessary. Some students might even, in fact, rewrite this as just 3 plus 5i plus 6 minus 3i. Set erase, please, and thank you. There you go. That's an unnecessary step for a lot of people, but if you want to rewrite it, you can. And then you just combine like terms. 3 plus 6 is 9. 5i minus 3i, just think of that as 5x minus 3x would be 2x. So that's plus 2i, and that's our answer. Now you might say, Mr. Beckner, wouldn't you write that as 2x plus 9 generally? And I'd say, yes, I would. But i's are not x's. It just kind of feels like it because I actually represents one specific number where X could represent any number. So the way we write complex numbers, as we said last time, was in an A plus BI form. We like the imaginary number to be second. Is it necessary? No. You could write this as 2i plus 9. My math lab would count it wrong. My math lab would count it right. I would count it right and no one would care. This is just tradition to write the I term second. And that's it. Easy peasy. Let's just change one tiny detail of this problem. Let's change that to a minus between the parentheses instead. Now this time, I do suggest that everybody takes the intermediate step to change this to being without the parentheses, but it's not the exact same thing as it was before. The 3 plus 5i is, but this minus counts as a -1 in front of the parentheses, which needs to be distributed. And this is where students go wrong half the time. They give the minus to the 6, but they don't give it to the 3i, and they'll leave this as a -3i when in fact it should be a +3i. It is such a simple mistake to make that so many students will make. I would flip a coin and say you'll make this mistake at some point. Guess what? I've made the mistake. Nobody's perfect. No human being is perfect. And then from there, like last time, just combine your like terms. But it's gonna be a little different this time. 3 minus 6, well, that gives us a -3. And then 5i plus 3i gives us a +8i. And there's our answer. Same values in the parentheses, but now no sign between them. No plus, no minus, no nothing, just parentheses. Excuse me. So here is where we have to do that thing I mentioned some students might have wanted to do with A. You have to FOIL this. You do have to FOIL this. Your first, outer, inner, last. Your 3 times 6, that's going to be an 18. I'll even write the FOIL above it. The outer, the 3 times the -3i would be a -9i. You're just multiplying the 3's. The inner, the 5i times the 6 is going to be a +30i, outer, inner. And then for our last, that's 5i times -3i. Read for wrong, 5i times -3i is -15i. Read for wrong, read for wrong, read for wrong. This is wrong. Why is that wrong? This is another common mistake that students make. What's x times x? It's not x, it's x squared. What's 2 times 2? It's not 2, it's 2 squared. What's 5 times 5? It's 5 squared. Yes, those are 4 and 25, but not the point. So what do you think I times I is? It's the same thing as what x times x would be in general. It would be I squared. So this is a -15i squared. Watch out for that. That's another mistake that students commonly make. And then you can combine your like terms if you want, but I'm going to pause on that. I'm going to leave the first 3 terms alone for now. 18 minus 9i plus 30i. And I'm going to change the last term because, you know, you couldn't change x squared, but you can change I squared. We said that the square root of -1 we were going to turn into i's. But we also said what I squared was. We said that I squared is -1 because when you square root, those cancel out, so you're just left with the inside. This is an extremely important value that you will see over and over and over and over and over. Every time you see an I squared, you have to change it. You have to change that to a -15 times -1. If you don't, it's wrong, 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 wrong. So that's a +15 here, the -15 times -1. So I am taking my sweet time here. Yes, I could have combined the I terms earlier. That's okay. I'm just waiting till I see pairs. So 18 plus 15 is going to be a 33. Then -9i plus 30i is going to be a +21i. That is our final answer. Again, I could have gone ahead and combined these 2 things earlier. I could have combined these 2 things earlier. That would have been acceptable. I just didn't. So what do you do whenever you see an I squared? You turn it into a -1. One more like this. Let's change the game a little. I'm getting sick of the 3 plus 5 and the 6 minus 3i. So 3 plus 4i times 3 minus 4i. And this problem right here, I'm going to put a little asterisk next to it because this one is super important, very important for what we're about to do, which is the division, which I said division has an exception of how we have to handle it. Because again, spoiler alerts, you can't really divide most complex numbers. But as I said, there's exceptions to every rule. Well, most rules. Well, this looks like a parentheses times a parentheses. So once again, we're going to FOIL. I'm going to skip writing the FOIL part from now on. The 3 times the 3 is going to be 9. The 3 times the negative 4i is a negative 12i. The 4i times the 3, that's the inner, is going to be a plus 12i. And then the 4i times the negative 4i is a negative 4i squared. Watch out for that I squared. Now you might have noticed something about this problem. 3 plus 4i, 3 minus 4i. There's kind of a symmetry here. There's like a mirror almost. But it's not a mirror. It's just one. It's an a plus b times a minus b formula. Something that we're going to talk about in factoring later. Something that if you're in my MDE, we've already talked about factoring with that. But it's got a very special property with real numbers and variables that actually carries over with imaginary numbers. So check this out. I squared becomes a negative 1. So this is 9 minus 12i plus 12i, and then minus 4 becomes negative 1. What do you notice about the outer and the inner here? Negative 12i, positive 12i. They're opposites. They cancel. And this is by design. So these two suckers cancel, and we're left with 9 plus 4, which is 13. Huh. We haven't seen that happen yet. I'm not saying it couldn't have happened yet, but we didn't see it happen yet. There's no I term here. This is entirely real. And this will happen every single time. This will always happen. Multiply a plus b, a minus b, no matter whether there's i's or not, outer and inner always cancel. If the b terms i's, you'll end up squared turns real because that's negative 1. Thus, will always have a real answer. Because the outer and the inner terms are going to be the ones that have the i's. The first term is a squared. That's just a real number times a real number. The second number is going to be the b squared, but with a change of sign because of the I squared becoming negative. And in fact, you can even write this as a formula. A plus bi times a minus bi is going to end up being a squared plus b squared. Notice that these have i's and this is a plus. This is not the difference of squares formula. This would actually be the sum of squares formula using imaginary numbers for factoring, something we're not going to do for a while. It's not really a formula I suggest that you memorize because you might goof and call it the difference of squares formula. But it is a formula that you could use if you are well practiced. So again, it always turns real. We're going to use this fact to trick division of complex numbers in general, we can't actually divide complex numbers. Why? Just trust me. Take a leap of faith. Call a plus b and a minus b conjugates. The conjugate of one is the other. So if you had 3 plus 5i, its conjugate would be 3 minus 5i. If you had 3 minus 7i, its conjugate would be 3 plus 7i. You just changed the sign of the second term. And it doesn't matter if they're imaginary or not. If you have 3 plus 5x, its conjugate would be 3 minus 5x. Or if you swap the order of those, 5x plus 3 has a conjugate of 5x minus 3. You just change the sign of the middle term. Our trick to divide complex numbers multiply top and bottom to get you have to do this top and bottom because you can't just change the bottom, you're changing what the value is. If you had, say, 2/3 and you multiply the bottom by 5, you've changed what the number is. But if you took 2/3 and multiplied top and bottom by 5, you haven't actually changed anything except visually. The number would be the same because 5 over 5 cancels. And so if you cancel it, did you really do anything? Well, that's why you don't actually cancel it. This is the trick for dividing complex numbers. You multiply top and bottom by the conjugate of the bottom. Don't even look at the top. Don't even look at the top. Don't even look at the top. When you're trying to figure out how to start this, cover up the top, look at the bottom and say, all right, whatever that middle sign is, just change it. And that's what I'm multiplying top and bottom by. It's a little bit of a memorization, but I've given you the rationale as to why we do it. Why? Wait, why are we doing this? Because it'll make the bottom number real. And we said that all complex numbers have to be written in an a plus bi format. We can't have i's in the bottom. So this trick will make sure we have no i's in the bottom because the bottom will always end up real. And we'll see this once we get to our example. Let me give you about another 30 seconds to write all this jazz down, and then we'll start into that. All right. Example 3. Let's see. See, I don't tell you do this and that and this and that. You have to know what to do when you see a problem like this. 4 over 2 minus 3i. This is what a division of a complex number looks like. You got i's in the bottom. I's are not allowed to be in the bottom. They can only be in tops. You can't have I squared. You can't have square roots of i's. You can't have i's in the bottoms. They can only be in the top. All answers can have a real number in an I number. That's it. But the I number can only be in the top. So we take the original piece, 4 over 2 minus 3i. Me, your math teacher, I have no idea how to divide 4 and 2 minus 3i. I'm not lying to you. I have no idea how to divide this. I have to use this trick. So we said i's aren't allowed in the bottom. Since the bottom has an imaginary number and it's of this form in a plus or a minus b, we can make it real by multiplying top and bottom by the conjugate. See, we really only need to do this in the bottom. If there was a way we could just do this in the bottom, that would clean up the bottom, and that's okay. But I'm changing this by just multiplying the bottom. I would be changing the value inherently. So whatever you do to the bottom, you do to the top. It's the exact same as with equations. Whatever you do to the left side, you do to the right side. So again, because this was a minus, this is a plus. Just change those signs. It's super simple. And from here, you just distribute and FOIL as necessary. For the top, you're distributing. 4 times 2 is 8. 4 times 3i would be 12i. And over. And in the bottom, you're going to be FOILing. First, 2 times 2 is 4. Like 2 different problems. The outer, 2 times the plus 3i would be a plus 6i. The inner, negative 3i times 2 would be a negative 6i. And then the last, negative 3i times positive 3i will be negative 9i squared. After you do a dozen of these, you might find yourself taking shortcuts like skipping the outer and the inner of the bottom. You always got to do it at the top, though. Because the outer and the inner and the bottom will always cancel. 6i, negative 6i, gone. This I squared becomes a negative 1. I can't really do anything in the top for now, at least. So 8 plus 12i over 4. Again, these will cancel. And that becomes a negative 9 times negative 1, which is 8 plus 12i over 4 plus 9, which is 8 plus 12i over 13. And this is our answer because there's no common factor in all three parts of that. If that bottom was, say, a 16, this would be reducible. I just want to show you what I mean there. Let's say that there happened to be a common factor in all three of these. You would say 4 goes into all of these. So you'd say 4 goes into 8 twice, 4 goes into 12 3 times, and 4 goes into 16 4 times. And this would be 2 plus 3i over 4. But that common factor has to be everywhere. If it's not everywhere, you can't reduce it as a fraction like that. You have to split it and reduce one of them. So here's the alternate way. If you don't like that, just split the fraction. 8 over 16 plus 12i over 16. 8 over 16 becomes a half. And then 12i over 16 becomes 3i over 4. In fact, you can see the first fraction is different. But both of these would be accurate answers. You can't say, oh, 2 and 4 reduces to 1 and 2, because the 3 doesn't cancel with them. That's how these compounded fractions work. So watch out for those types of simplifications. Wrong color. All right, one more. 3 minus 4i over 4 plus 3i. I can't cancel these 4s. I can't cancel these 3s. Once again, multiply by the conjugate. And it's technically called the complex conjugate because of the i's of the bottom. So the 4 plus 3i, that means we multiply by 4 minus 3i, top and bottom. We will then FOIL. We have to FOIL the top and the bottom. There are shortcuts to the bottom, but not the top. I'm not going to take either of those shortcuts. I'm just going to complete the FOIL. So let's just pretend like the bottom's not even there. So just pretend. Can't see the bottom for now. Just focus on the 3 minus 4i times the 4 minus 3i. So 3 times 4 is 12. 3 times negative 3i is negative 9i. Negative 4i times 4 is a plus 16i. Then negative 4i times negative 3i, watch your signs, is a positive 12i squared. Don't forget your square. Did I goof somewhere? I did goof somewhere, didn't I? That negative 4i times 4, that shouldn't have been a plus 16i. That's supposed to be a minus 16i. Make sure you get that right. So again, 3 times 4 was positive 12. 3 times negative 3i was negative 9i. Negative 4i times 4 is negative 16i. I was going too quick. I apologize. And then the negative 4i and the negative 3i make that a plus 12i squared. For the bottom, 4 times 4 is 16. That's our first. The outer, 4 times negative 3i is a negative 12i. Now, before I even look at anything on the left side, I'll bet you $1 million the next term is positive 12i. And sure enough, 3i times 4 is a plus 12i. And then 3i times negative 3i is negative 9i squared. Let's go ahead and combine our like terms as well as switch the I squared to negative 1. So this is 12 minus 25i, that's negative 9 minus 6. That will be a plus 12 times negative 1 because I squared is negative 1. Over 16, the outer and the inner cancel, and that's by design. Then a minus 9 times negative 1. That's 12 minus 25i minus 12 over 16 plus 9. Check this out in the top. 12s actually cancel. That's kind of cool. Doesn't happen a lot, but it does here. So minus 25i over 16 plus 9 is 25. Here the 25s cancel because there's no real term. There's no multiple parts. This is just a nice simple fraction. You get negative I. You could draw a very, very, very specific conclusion with this problem that if you had an a minus bi over b plus ai, the whole thing always simplifies to negative I. I wouldn't bother because you might only see that one more time in your entire life. But it is a cool symmetry problem. So do these answers always have to be fractions and have a real and imaginary part? No, they can just have real parts. They can just have imaginary parts. Do they usually have both parts? Yes, in fact, they do. All right, last part of this section. And there's kind of a special note here. Multiplying several square roots of negatives. Must pull out the i's. First. This is kind of like a PEMDAS issue. And I'll even show you that you would think there's two different answers, but only one of them's right. When you're multiplying several square roots of negatives, so if I had like a square root of a -7 times a square root of a -3, you would say, oh, okay, we'll just go ahead and squeeze the insides together. You told us the square root of a times the square root of b is the same thing as the square root of ab. Yes, except with imaginary numbers. You have to pull out the i's first. It has to do with the order of operations of imaginary numbers. This is really the only one we have of importance at our level. For I, we're going to have 3 square roots of -5 times 4 square roots of -3. I will admit the parentheses here are completely unnecessary, but I'm doing them anyways. So here's the way you have to do this. You have to do this. You have to do this. You have to pull out your i's first. I know that sounds gross. So you cannot take the -5 and the -3 and say that's a 15. It's wrong, 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 wrong. You have to make this 3i square root of 5 because you're just pulling out the square root of a negative times 4i square root of 3. You have to do this first. If you don't do this first, you will get a wrong answer. I guarantee it. Now what do? Well, this is just a big product, so we multiply outsides and we multiply insides. It has nothing to do with FOILing. It just has to do with the normal operation of multiplying values with and without radicals. So we take the 3i times the 4i, which is 12i squared. I times I is I squared. And then under the square roots, 5 times 3 is 15. But I squared is -1. It's too far. So that's 12 times -1 times the square root of 15, which is -12 square root of 15. I'm going to show you the wrong way. If you had done 3 square root of -5, and I won't erase this, times 4 square root of -3. If you had done the insides first, 3 times 4 is 12, -5 times -3 is positive 15. You would have gotten 12 square root of 15, and you would have boxed this up and shipped it out. But guess what? You're missing the negative. That's what happens if you don't pull out your i's first. You end up losing a factor of negative. You get the opposite of the correct answer. That's what happens if you do it in the wrong order. So please, please, please be careful. Is this something you're going to see all semester? Honestly, no. Is this something you'll probably see a couple homework problems and a test problem on? Yeah. Is this something that if you're going to take several semesters of math and keep trucking through calculus that you'll see? Yes. And that's kind of the slight annoyance of pre-calculus. There's going to be a lot of things that you're going to keep using throughout this semester, throughout Calc 1, throughout Calc 2. But then there's going to be other things that you might not see for a year or two, and you've got plenty of time to forget it, and you've got to dust off that pre-calc book and your notes and stuff later. But that's just a fact of life. A lot of the times we go through things without using them immediately. But it's still an important technique to practice for now, and maybe you'll remember it for later. All right, one more for the section. 2 square root of negative 8 is 5 square root of negative 2. Now again, we have to do this the right way. We have to pull out the i's first. So this would be 2i square root of 8 times 5i square root of 2. If you don't, you will have the negative of the correct answer at the end at best. Multiply the outsides. 2i times 5i is going to give us a 10i, inflection in voice. No, 10i squared. I times I is I squared. Then under the square root, you might say, oh, well, I could have made that square root of 8 4 times 2. Square root of 4 is 2, so it's 2 square root of 2. Sure, you can, but there's going to be something magical that happens with this one, so you don't have to do that. 8 times 2 is 16, and we know the square root is 16. This is 10 times negative 1 because the I squared is negative 1. And the square root of 16 is 4, so that's times 4. 10 times negative 1 is negative 10, times 4 is negative 40. Boom, there we are. So these are our complex numbers. These are our imaginary numbers paired with real numbers. Now, here's the thing. All numbers you ever deal with in the world are complex. The number 7. Real, but all real numbers are complex. 5i is complex. Purely imaginary. Kind of like saying apples are fruits, oranges are fruits. So when I have an orange, I can call it an orange or I can call it a fruit because it falls into 2 classifications. A fruit is the wider classification, and orange is more specific. So saying 7 is real is more specific. Saying it's complex is more of a blanket statement. Saying 5i is imaginary is more specific. Saying 5i is complex is less specific, more of a blanket statement. So all numbers you ever deal with in your entire life are complex. Just some of them we can name more specifically, just real or just imaginary. So that'll close out 1.4. So that homework is due in a week. We will definitely not finish 1.5 today. We're honestly not even going to start it because like I said, we're going to do a factoring review. And unfortunately, I have something going on in my house in about 10 minutes, 5 minutes, 10 minutes. So what I did today is I'm just going to pull my video from a factoring review from a previous semester. It's something I did not want to do for this course, but it's convenient for us right now. Otherwise, I was going to have to kill the lecture right now. So if you have any questions per usual, you can ask in the chat. It just might take me a couple minutes to get to them because I'm not going to be in front of my screen the entire time, but you will still get the exact same information I was going to do. It's just in a video format. So give me about 30 seconds to set that up.
All right, so 1.5, quadratic equations. We're going to study these from a few different angles. We're going to solve them in a few different ways, more specifically. And the first thing that we're going to approach that with, the first technique, is going to be factoring. Now, the top of the notes for this, I just have see factoring document. Now, I'm not saying that you're going to look at it outside of class. I am going to actually review this. I said that I would eventually. This is not going to be a super in-depth review. I was looking at it earlier, make sure I had everything in place. But this is all of the different types of factoring that I don't want to say that you can use, but that would get the job done. So if you have ways of completing a problem where it requires factoring and you didn't do it via a way I say, guess what? That's completely fine. There are lots of different factoring methods. I have never learned all of them because there's literally hundreds. I have actually once or twice in my life had a student introduce a method to me that I had not seen before, and I might like it. It might have its quirks, problems, successes, all sorts of things. So you go with what you're comfortable with. But the point is, you are pre-calculus students who have been taught factoring previously. At least you should have, otherwise you probably shouldn't be pre-calculus students. And you are supposed to have retained that knowledge. Now, we understand that retaining math means you probably didn't use it for a few months and you've half forgotten it already. So that's why we give you these quick little brush ups, touch ups. I don't know what I was trying to say there, but I like to give quick reviews, or at least give you access to documents and web pages and things like that, and extra homework assignments that you can take the time on your own. So let's get into it. The first major factoring kind of tactic is using a formula. And we're generally trying to use formulas for binomials. What's a binomial? Well, it has that prefix or prefix of bi, which means two. So binomials are polynomials with two terms. Something like, you can see an example, x cubed plus 64 right here. So that has two terms because it's this thing and this thing separated by pluses or minuses. So you have three very common formulas. You'll notice that there's four things up here, but I said three common formulas. That's because the second one is not really a formula. The difference of squares. If you don't have this memorized yesterday, that's a problem. And I'm exaggerating with the yesterday, you know, I'm a little silly. But you need to have this one memorized today, tomorrow, every day of class. If you're gonna go into calculus, this one's not going away. Most of the stuff isn't going away, honestly. I really try to be honest with you about what you will see again and what you might not see again. Usually I emphasize what you'll see again, and then you can use process of elimination from there. But difference of squares. So if you have something like x squared minus 9, or x squared minus 25, or x squared minus 36, and it doesn't have to just be x squared, it could be 4x squared, or it could be 4x squared minus 64y squared. You can have variables and numbers in both terms. Whenever you think you've got that kind of setup, you have to factor this as a plus b times a minus b, where a and b are the square roots of the original terms, if you want to be technical. But what most people just say is they're trying to come up with something that when you square it, you get the original terms. So for instance, x squared minus 9 would factor to be x plus 3 times x minus 3. That's weird. No. I got a bad feeling. I think I have had this happen once before. Let's try closing and opening. Let's see if it was working in the other one. It's working in this one at least. So I can always just write somewhere else. Factoring. Oh, hey, let's have one weird thing lead to another. Well, either way. There we go. Okay. Technology, am I right? So something like x squared. I wanted that in red though. Why? I'm just messing this up even worse. I think I fixed it. Fingers crossed. All right, so if you had something like x squared minus 9, the factored form would be x plus 3 times x minus 3, something like that. Because x squared is, it sounds redundant, x squared and 3 squared is 9. That's when there's a minus between them. When there's a plus, you can't factor it using real numbers. Please notice how I just said that. The sum of squares is prime in terms of real numbers. So if you had x squared plus 9, what you would say for now in this course, notice I'm saying for now, is it would be x squared plus 9. You couldn't factor it. You just call it prime. In terms of solving it as a quadratic equation, we have to go another route besides factoring. And that's the thing about these polynomials. If you were to just randomly create or randomly find a polynomial in the wildlife, just scurrying around, there's about a 95 to 98% chance it's not even factorable. Most polynomials are prime. But you might say, well, that doesn't feel right because in my math classes, almost all of them have been factorable. And that's because we are designing them to be factorable. In the real world, when things can be chaotic and disorderly, if you just have random numbers, usually they're not factorable. So this idea of being prime is actually pretty common when you deal with the real world. So if you're trying to solve by factoring, but it's prime, you can't solve by factoring, so you'll need alternative methods, which we'll get into. So sum of squares, for now, we say it's prime. By chapter, 3, we'll learn a way to factor using imaginary numbers, but we won't really use it too much at this level. Then you have the sum of cubes and difference of cubes, and these two pair together. You should really memorize these as a pair because you look at this a squared, ab, b squared. There's a lot more going on the right-hand side versus the difference of squares. And a lot of students will try and memorize these independently. I'll be honest, when I had algebra, I think I saw this formula the first time in Algebra 2. My teacher didn't tell us to memorize them as a pair. They said memorize them one by one, and it was annoying. I didn't like it. But if you really kind of make an observation, half of it's pretty easy to remember because the a squared, ab, b squared pattern is the same in each of these. Whether it's a sum of cubes or a difference of cubes. See, there's no prime going on here, and it has everything to do with the even or oddness of the exponents. Remember, an I comes from a square root of -1. But these are cubes, so trying to solve it feels like a cube root, which it's okay to have negatives of. All right, so it doesn't matter if this one's a plus or minus. It's the cubes where it does. Minus okay, plus no. So a squared, ab, b squared. That's the a-b pattern, no matter whether it's a plus or minus. Then I've got this nice little mnemonic device, kind of like foiling or PEMDAS. I use what I call SOAP. Yes, your math teacher is telling you how to use SOAP, my classic joke. So SOAP stands for same, opposite, always positive. It tells you the order of these signs. The first sign is the same as the original sign. So if it's originally plus, the first one's a plus. If it's originally a minus, the second one's a minus. By the way, if you're not writing all this down, that scares me, especially if you're weak when you're factoring. The O stands for opposite, so the second sign is opposite of the first sign. So if the first one's plus, the second's minus. If the first one's minus, the second one's plus. And the last one is AP, always positive. So the last one goes together, always positive. No matter what, the third one is always positive. And if you don't trust these formulas, if you want to go through and be meticulous, multiply out the right-hand side. You'll have 6 products to do. You'll see a lot of canceling, and you'll end up with the a cubed plus b cubed or a cubed minus b cubed, whichever it's supposed to be. You have got to have all 3 of these formulas memorized all semester. When you go on to calculus, you're going to need those formulas memorized all semester. If you're going on to pre-calc 2 before calculus, depending on the type of calculus you take, guess what? These formulas will pop up in there every now and then. Even though it's trigonometry, you'll still see it occasionally. You never, ever get to forget these formulas the rest of your life in math. Now, when you stop taking math classes, if you don't have a career involving this stuff, sure, forget it then. So I didn't give any examples of difference of squares here, but I did write one really quickly in red up there. But down here, I did give an example of a sum of cubes. The only difference here would be the signs if I made that a minus 64. So this is the process I go through. Now, if you think differently, if you operate differently, you do your own thing as long as you can get to the answer. But here's the way I do it. X cubed plus 64. This 3 tells me I should be doing the cubes formulas, not the squares formulas. So A would be the X, because if you cube X, you get X cubed. And B would be 4, because if you cube 4, you get 64. Again, it's like taking a cube root of what you see there. So we take the original thing, and all I do is A squared, AB, B squared. Now I went ahead and swapped the order of the 4 and the x. So the a times b would be x times 4, but we of course want to write 4 times x instead. It's just more proper. But I did not put any signs in between these terms yet, because it didn't matter what this was. If it was plus or minus, this right here, this binomial and trinomial would be exactly the same. The 16 was the 4 squared, by the way. 4 squared is 16. So because that's a plus though, then we can use SOAP, same, opposite, always positive, to get the signs correct. And again, if you don't like my mnemonic device, you don't have to use it as long as you got a way to get it right. So SOAP, same, says the first one should be a positive, so we make it a plus. Opposite says the second one should be a minus, and the third is always positive no matter what. So if we had x cubed minus 64 instead, there was a minus, it still would have gone x 4, x squared, 4x, and then b squared, the 4 squared is 16. That is exactly the same. But what would be unique is these signs would be different. The first would be the same as the original, so minus. The second would be the opposite of the original, so plus. The third would be always positive. Practice this. If you're rusty with it, or for some reason you've never factored cubics before, which terrifies me, again. And I bring these points up because of this self-enrollment process that we have at TCC now. It's possible that you put yourself in this class without having the necessary prereqs, because they don't tell you, well, no, you didn't take this, so you can't take that. You can just say, hey, put me in pre-calc, doc. Maybe you shouldn't be here. I don't know. I haven't had, hour-long conversations with every single one of y'all. That's what the counselors are supposed to be doing to put you in the right place. So again, I'm not trying to terrify everyone. I'm just trying to make people aware that you could be lacking some of the things that you're not supposed to be lacking in here. In which case, if you want to stay and try and keep up, you've got to fill in the blank, so to speak, and do those extra assignments, go to the internet for extra work, go to tutoring, whatever you have to do. I sent the tutoring. Yes, I did send the tutoring document. Okay, cool. So those are our binomials. Now, there are formulas for some trinomials, things with 3 terms. So I'm going to kind of add something to the side here, that we have some formulas for trinomials. And that's I'm writing the wrong side, I'm swapping my left and right side. It goes a squared plus 2ab plus b squared is equal to a plus b in parentheses squared, and a squared minus 2ab plus b squared is equal to a minus b squared in parentheses. So these are what we call our perfect square trinomials. We will actually use the idea of this for something known as completing the square, but we don't really manually do this factoring hardly ever. Sorry, I got stalled out there in my thought process. The stuff I'm going to show you is what would generally be usable. Anytime you actually have to use this formula, we kind of just pull it out of thin air, as we'll see in examples later. Okay, so factoring trinomials. I'm going to give you 2 primary methods. The naming convention I have for them are the shortcut method and the AC method. Some people call the AC method grouping because that's one of the things you do in it. Also, I call it the AC method because that's one of the things you do in it. The reason I call this first one the shortcut method is because it's a shortcut of the AC or grouping method. Some of you may have heard of the box method. Some of you may have heard of, I think it's called the push and pull method. I'm not going to be teaching those. Again, if you are fluent in them, use them. I don't care, but I'm not going to teach 50 different ways to factor something. The third primary factoring method that's classically taught is trial and error. I'll describe it. I don't really emphasize it a lot because it's something that you need to do hundreds of times to get really, really good at. Whereas this AC method I'll give you, you really only have to do maybe 10 to get really good at. And it's just because it's a lot less of a guessing game. So I'll explain that when we get there. All right, so shortcut method. List the pairs of numbers that multiply to make C, but add or subtract. Add if it's positive, subtract if it's negative to make B. And when I say it, I mean the constant at the end. So when I say factor something like x squared plus 5x, I'm sorry, x squared plus bx plus c, I'm saying something like x squared plus 5x minus 6. These don't have to be all pluses. You can have minus signs wherever. The main idea is that the leading coefficient is 1. There is no number in front of that x squared. I'm not saying that's a 0. I'm saying there's no number in front of the x squared. When there's no number in front of the x squared, you can use a shortcut approach. So you're taking this number along with its sign at the end. This will be a constant. And that's what we're doing in step 1. We're writing all pairs of numbers that multiply to make that. And you're going to try and find a pair that adds or subtracts to make the middle number. We're trying to make this number. We're finding pairs of numbers that multiply to the red thing, but add or subtract to the blue thing. How do you know whether you're adding or subtracting? It's based on the red number's sign, the C's sign. So you'll give them signs based on it to make the B. That's what I was talking about with the blue. So the blue is trying to make the numbers appropriately to that. And then your factored form is always x number with a plus or a minus. I'm not using an actual plus or minus symbol. I'm saying it's one or the other, but I can't type that in Word appropriately. So it's something like x plus 3 times x minus 5. And the numbers are what you chose between steps 1 and 2. So the example I give is and I'm actually going to give a little space to show you how I write this out personally, which again, you don't have to. So for x squared plus 5x minus 6, what I do is we take this number, including its sign, and I'm going to write it to the side. And I draw a little upside down V, and then I'm going to write all the numbers that multiply it to 6. 1 times 6 or 2 times 3. And you can see that explanation below, but I'm just showing you how I do it by hand. So that's step 1. Notice I wrote the sign. Even if this was a plus, if this was a plus 6, I would have written the plus here because we're going to need that to tell us whether we're adding or subtracting in the next instance. But it was a minus, so let's leave it that way. So then we're going to try and make sure that they are, since this is a minus, we're subtracting to try and make the 5, and it's got to be a positive 5. Because 1 and 6 and 2 and 3, it seems like either option could work, because 6 minus 1 is 5, but 2 plus 3 is 5. But this sign means that the product has to be negative. They have to multiply to make a negative 6, whatever we choose. So if you choose the 2 and 3, 2 times 3 is 6. If you choose these both positive to make them add to a positive 5, well, positive 2 times positive 3 is positive 6, not negative 6. Remember how I said that you need to be really good at your arithmetic with signs and that your calculator's not going to save you? Because there's something that you're going to have to just have this implicitly known very well. This is what I'm referring to. Factoring is where your sign math has to be in your brain. You have to be decent at this. Your calculator is not going to save you. It can, but it's going to take you 5 times as long to do it probably, and that's not good. All right, so we're trying to make a positive 5. So we're trying to make a positive 5, but the product has to be negative. If I choose 6 and 1 to make a 5, I'd have to have opposites, positive 6 and negative 1. So that's out. 2 and 3, you know what? I was looking at a plus sign, excuse me. I was looking at something else. I was looking at this when I said that, pardon me. That's what I don't like about this teaching method. All right, this minus says we're supposed to subtract them as I said. If we subtract 6 and 1, we get 5. If we subtract 3 and 2, we get 1. So 1 and 6 is actually our choice, again, because we're supposed to be subtracting the pairs because this was a negative. But then we have to give them signs to make sure they add to a positive 5. So they have to be opposite signs. I'm going to do this wrong at first. If I go negative 6 and positive 1, well, 1 minus 6 is negative 5, not positive 5. So I need to swap those signs. It needs to be a positive 6 and a negative 1. So therefore the answer is x in the first spot of each parentheses, and then a minus 1 and a plus 6. Now check this out. You can go minus 1 and then plus 6, or you can put them in the opposite order. You can put the plus 6 first and the minus 1 last. It doesn't matter. I like to go in the order I see though, so I'll keep it the original way. So again, there's all the typed up explanation you would have seen in your notes already. But this is how it looks by hand. If you're not doing this upside down V stuff, if you're not showing this side work at all, if you are good enough to go straight to the factored form and you get it right 100% of the time, then we're cool. I don't need you to show the work. If you're struggling, if you're getting them right 75% of the time or even worse, then you need to show your work and you need to practice, because this factoring stuff is going to be just a minor step in a much bigger game. So that's our shortcut method, when the leading coefficient is a 1, when there's no number in front of it. Next up we have, I'm just going to hit enter a couple of times so we can see all this, the AC method. Again, please write this stuff down. Don't just look at it and think you've memorized it already. That's probably not the case for most of you. Take good notes. Oh, but Mr. Beckner, you typed this up for us. I can just read it later. If you learn by writing, that's not going to help you. If you're terrible at organization, it's not going to help you. I have a feeling organization is lacking for some of us in these times, having to work in much different conditions. And it's understandable, but we have to do our best. So the AC method is called the AC method because in the first step, you're going to multiply the A and the C, the leading coefficient and the constant. That's what they are known for. That's why it's called the AC method. So the AC method is called that because you multiply A and C. This was one of the shortcuts in the previous method. All we did was just use the C. Now we got to use the A times the C for some reason that you just want to trust me on. I explain why in an Algebra 2 class, but we don't have time for that explanation here. Then you list the pairs of numbers that multiply to make this value, but add or subtract. Same, add if it's positive, subtract if it's negative, make B. This step is literally the same step as what step 1 was in the shortcut method. List the pairs of numbers, multiply, blah, 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 blah. List the pairs of numbers, blah, 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 blah. Exactly the same thing. It's just instead of only using the constant at the end, you have to multiply the leading coefficient and the constant. The reason the shortcut method works in that regard is because the leading coefficient's a 1, so 1 times the constant will always be the constant. So this is the exact same thing we did before. Here's where things change. Instead of, and this is the real shortcut of the shortcut method. The shortcut method says we went straight to the answer. Oh, it's just x's in the first slots and the numbers in the second slots. When that leading coefficient is a 1, you might have numbers that need to go here, like a 2 and a 5, something like that. So we can't just use this approach. So what we have to do is, and again, give them the signs based on combining to B, but you have to split the middle term into 2 terms. You are going to create a 4-term polynomial. You're going to take something that had 3 terms and make it 4. And you might go, well, why on earth would we ever want to do that? That seems completely unreasonable and silly. Why would you take 3 terms and make them 4? Because there's going to be something that as long as you can make it this far, I 100% guarantee that the problem you can finish factoring by doing something known as grouping. What is factor by grouping? Because that technique is specifically for 4-term polynomials, unless you say factor by grouping for 3-term polynomials. See below, we'll see below. So factor by grouping for once you have your 4 terms, which again is needed for the AC method. So this is part of the AC method, but it can also be its own problem. I can give you a 4-term polynomial, and the only way you'll know how to factor at this level is by grouping. So you take the GCF from the first 2 terms. You take the GCF from the last 2 terms, greatest common factor. So we're mentally going to split these things in half. First 2 terms, take out a GCF. Last 2 terms, take out a GCF. Now, with the last 2 terms, you'll also have to take out a sign. You'll have to take out a plus or a minus because, well, it would look wrong otherwise. The reason you don't have to do it for the first part is because there's nothing that's going to be in front of the first GCF. So you don't have to write a plus. I'm going to give you a super hint for that, that I do not have typed up there. Good. If the parentheses match, which is what you're hoping for, then the parentheses is a 3rd GCF. I'll show you, well, you can see it right here. This step 3 is exactly what we're talking about right here. So pretend like you don't see this yet. So after you do steps 1 and 2, you'll end up with something that looks like this. So here was your GCF from the first term. Here was your GCF from the second term. So let's ignore all of this stuff for now. We're just looking here where it says so. This 5x minus 1 is part of the first term. This 5x minus 1 is part of the second term. It is a product that is in two terms, which means it is a common factor. Product means factor. So that would mean your GCF is that parentheses, 5x minus 1. So whenever you have a GCF, you write it first, then you open another parentheses and you write what's left over. And after you write what's left over, it turns out this is what you get. So here's your GCF of your 5x minus 1. There we go. Then you open up your parentheses. And what goes in here, what I do is I say just use your hands to cover up the GCF in the previous line. So where we have all the blue and red ink right here. So me covering this with black ink is going to be me covering it with my hand. So this is me covering the 5x minus 1 with my hand. This is me covering the 5x minus 1 with my hand. What do you see left over? You see this x and this minus 3, and that's exactly what goes in the other parentheses, x minus 3. That's the easy way to factor out a binomial GCF. Write it first, just like with any GCF. Open your new parentheses. Mentally cover up the GCFs in the previous line. Whatever you have left over is what goes in the next parentheses. And if you don't trust this, you can FOIL everything out and you should get the original equation. So that's factor by grouping. And then that hint I gave you for step 2. If the third term has a negative, it's 99% likely you need to factor it out. I'm estimating with the 99%, but it's really freaking close to all the time. So that's a super awesome hint for, all right, what sign do I take out for the last two? Do I take out a plus or a minus? What you can do is what I call the productive struggle, where you just take out a plus, and if the parentheses don't match, go back and take a minus instead, because that'll probably fix it. But the hint will help you skip wasting time and just say, all right, if the middle term's got a negative sign, then that means you need to pop out a negative. And that's 99% effective. You know, plus or minus 1%, something like that. Maybe 98, maybe 99.5, I don't know. You get the idea. In Math 161, it'll work all the time. That's what I'm trying to say. In the real world, it's going to fail once or twice. All right, so once again, this factor by grouping, this is its own process. So what I'm going to do really quickly is one example of just factor by grouping, not the AC method. This is my favorite example to do, x squared plus 2x minus 4x minus 8. So this is 4 terms, 1, 2, 3, 4 terms. There are more factoring methods for 4-term polynomials. We don't need them in this class. You won't need them in this class, I promise. 1, 2, 3, 4. Is that right? Yeah, that's right. And you might say, oh, we'll combine the middle terms. No, don't do that. I've set this up for a reason. This might be x cubed plus 2x squared minus 4x minus 8. That would be setting it up so you didn't have like terms, but I want to go ahead to this point. All right, so for the first pair, the GCF would be x. Between x squared and 2x, the GCF is an x. So when I take out that x squared divided by x is x, and positive 2x divided by x is a plus 2. Now this is our goal for the next parentheses. If we can't make the next parentheses that in some way, shape, or form, it's not factorable for us. But I can guarantee you any problem you see, it will happen if that was the point of the problem. All right, now for the second one, you have to take out a sign, either a plus or a minus. I'm going to do this wrong at first. And I'd say red for wrong, but I'm going to keep it red once it's right. So this is wrong for now. I'm going to try taking out a plus. And then between 4x and 8, the GCF would be 4. When I do that, I have negative 4x. Watch your signs. This is negative 4x divided by positive 4, which is negative x. I was trying to write a 4 there, and that's not what it is. It's negative x. And then negative 8 divided by positive 4 is a negative 2. This and this are not the same. But you might notice they're almost the same. They have the same x and 2, but different signs. So that's what I called the productive struggle, where instead of taking out a positive 4, let's try and take out a negative 4 instead. So the red's not wrong anymore. This will be correct. Now divide out that negative. That negative is part of the GCF. So negative 4x divided by negative 4 is positive x. Negative 8 divided by negative 4 is positive 2. Now they match, so our third GCF is x plus 2. So what we do is we write that common GCF first. We then open up a new parentheses, and what's going to go in this is everything that wasn't the GCF originally. So cover up with your hands or your eyes or whatever those GCF parentheses. What do you see left over? An x and a minus 4. So that's what goes here. Now I don't want to leave the scribbling there, so I'm going to uncover my hands now. The x and the minus 4. Again, that was the x and the minus 4. So color-coded. Now, will you see a lot of factoring with 4-term polynomials in this course just out of the gate? No, it's pretty rare, maybe 5 to 10 throughout the semester in total. Let's say 10. But if you're going to go with what I call this AC method, this is part of the AC method, so you're going to have it down. Now, maybe you don't like this AC method. Maybe you go with the box method or the push and pull method or trial and error, which I specifically point out here that is an alternate method. I don't care how you factor, as long as you can factor. So if you love trial and error, use trial and error. I'll even be honest, when I'm factoring on my own, when I'm not teaching, I do trial and error 99% of the time. It's very rare that I do the AC method. But as a teacher, as a quicker tool, the AC method is easier to just pick up, because with trial and error, its namesake is exact. You might have 20 different options for a solution for the factored form, and you might get it right on the 20th try. And that's frustrating, because the person next to you might get it right on the first try, and they just have better luck. And we don't like luck coming into this too much, but hey, life's always about luck just a little bit. The AC method, there's no luck. If it takes you 4 minutes to do one problem, it's going to take you 4 minutes to do pretty much any problem. Whereas trial and error, you might do one problem in 30 seconds and then the next one in 15 minutes. Now, if you're someone who's done trial and error 300 times, you're probably pretty efficient at it and don't really need the AC method. However, you might come across a problem where the trial and error method is just a nightmare because there's 200 options, and you go, well, maybe I should try the AC method instead. It's good to have options. So don't be stubborn and set in your ways. Maybe try learning the new method as well if you've never seen it before. All right, so multiply the A and the C. List the pairs to make the B. Adding and subtracting is appropriate. Then you'll give those numbers appropriate signs. It's all really part of the same step. But then you split the middle term. So you might take something that's originally said a plus 5x and turn it into 6x minus 1x. You'll now have a 4-term polynomial that you factor by grouping. So let's try out this example, 5x squared minus 16x plus 3. I am taking way too much time to do this, unfortunately. That's okay. That's okay. So I'm going to do the AC method. We take the 5 times the 3. I even like to spell it out. So AC equals 5 times 3. If there was a negative 5 and a negative 3, I'd include their signs. 5 times 3 is positive 15. Remember, this sign is important because it's going to be telling you whether to add or subtract the pairs. So try and write it. List the pairs, so 1 times 15 or 3 times 5. Now find the pair that adds to make the middle number negative 16. Well, 1 plus 15 is 16, 3 plus 5 is 8, so we need to choose the 1 and the 15. But we also need to give them signs. Give these two numbers signs based on adding or subtracting to the B. So we need to make them add to a negative 16. If we make them both positive, 1 plus 15 is 16. But it's positive 16, so that's not going to work. They're both going to have to be negative. Now you might say, why can't they be opposite signs? Because then the product would be negative and the product has to be positive. This sign is the sign of the product. So again, there's a lot of sign math going on all at once that you have got to be masters of. Now this does not say the answer is x minus 1 times x minus 15. That's wrong. This is where we're splitting the middle term. So we go equals 5x squared. You don't have to write the 1, but I will for detail. minus 1x. Now, whatever this had is what goes with the 1 and the 15. And then minus 15x, then the plus 3. See this minus 16x, I have split into minus 1x and minus 15x. If you recombine them, you'll get the original problem, but do not do that because then you're going in circle, you're chasing your tail. Now we factor by grouping. We take a GCF out of the first pair. Between 5x squared and 1x, you can only take an x out. 5x squared divided by x is 5x. Negative 1x divided by x is a negative 1, not a blank, not a 0. I gave you that hint previously that said whatever the middle sign is, the sign of the third number, that's generally what you need for your GCF. So because that's a negative, I'm going to take a negative GCF out. Between 15x and 3, the biggest thing that goes into that is 3. Open parentheses. Watch your signs. If you don't pay attention, you might make a mistake. Negative 15x divided by negative 3 is positive 5x. That's good so far. Positive 3 divided by negative 3 is negative 1. Our parentheses match, which means it's a third GCF. So we pop out the 5x minus 1. We then open another parentheses, and inside of this goes everything that wasn't the GCF above. So cover up those parentheses with your hands. This is me covering up my parentheses. All I see left over is x minus 3. So that's what goes in the next parentheses, x minus 3. We can see the same thing typed below. I will unscribble some stuff now. Again, those were in your type notes already. Same answer, 5x minus 1, x minus 3. The order of the parentheses, once again, don't matter. You could write it like this, x minus 3 times 5x minus 1. Same answer, nobody cares ever. It's perfectly fine. (5x squared minus 16x plus 3). Okay, so let me show you what trial and error would look like for this problem, which is actually a very short trial and error. Let me not do it that way. Let me just do, I'm gonna do this. Nope, not that. And it's fine. I'm not gonna be saving that document anyways. So trial and error, T and E for trial and error. No, what are you doing to me? Draw. T and E. And this was for 5x squared minus 16x plus 3. Right, 5x squared. Yeah, minus 16x plus 3. So trial and error looks a little different. You're still going to be splitting up numbers into pairs of multiples, but you do it for the A and the C instead. So for the A, that's splitting up 5, which is 5 times 1. For the C, that's splitting up 3, which is 1 times 3. And then you're just going to use these numbers in pairs of parentheses. The 5 and the 1 would go with the x in the first slot. The 1 and the 3 would go just to the numbers in the second slot. But you have to swap things around. So it could be 5x times 1x. Let me do these in black, actually. 5, 1. And then the other one, we'll put the 1 and the 3 here. So the 1 could go there and the 3 could go there. Or it could be 5x, 1x, the 1 and the 3 could be swapped. Now, if you're swapping the latter pair, you don't have to swap the former pair, so I don't have to try swapping the 5 and the 1 because that would just replicate one of the other two scenarios. Now, if both of these scenarios fail, then maybe you have another option. So if this number was, say, 15, you could go 1 and 15 or 3 and 5. So maybe the 1 and the 15 fail in that order. Maybe they fail 15 and then 1. So then you got to try the 3 and the 5 and the 5 and the 3. But this is an easy one because there's only one option in for each of these. So then you just got to give pluses and minuses to make all the arithmetic work out. So the product has to be positive, which means these have to both be the same sign. If this was a negative, they'd have to be opposite. And again, that's just under the idea of multiplying two positives, two negatives, or opposites, and how they give us signs. but we got to make sure that the sum comes out to a negative. So if they have to be the same sign, but the sum is negative, that means they'd have to both be negatives. And then you can just FOIL this out to check. So you get 5x times 1x is 5x squared. 5x times negative 3 is negative 15x. Negative 1 times negative, so positive 1 is a negative 1x. Negative 1 times negative 3 is positive 3. When you combine, you get 5x squared minus 16x plus 3. And we actually got the answer right on the first try. So that trial and error was awesome because we got it right on the first try. Maybe another student did this one first. Maybe they tried the second one first and they got 5x squared, then times a minus 5x, then minus 3x, then a plus 3, which would have given us 5x squared minus 8x plus 3, which is wrong. So again, someone could have tried the second one first, got it wrong, and then went and did it the first way and got it right. There was only 2 trials to do here. There are plenty of trinomials that have 20 or 30 or 40 or 50 or 60 different trials though. Trial and error sucks for them. I would say on average for this course, it's usually in the ballpark of 8 to 16 options. But even that's pretty bad. But if you've done this a lot, you might have cases that are very obvious to throw out and you don't have to worry. All right, so that's our extended factoring discussion.
So that is where we're going to leave things today. So that's about time in this last little minute. I'm just going to remind you that we said 1.4 was going to be due on the 1st. We technically didn't even really start 1.5, but we did at least review material that would be important for it. I do not anticipate finishing 1.5 next time. It's a pretty long section. We might get close to the end. We'll get close to the end. Maybe we'll finish, maybe we won't. I'm not exactly sure. I feel like that usually takes about an hour and a half, hour and 40 minutes to finish that section. If we do manage to finish it, then I'll say 1.5 would be due in a week, but I'm not anticipating it for now, but we'll find out next time. All right, so as usual, if you have any questions, you can shoot me an email. We will see you on Thursday. I have not heard whether we're going to be continuing Zoom or not, so I'm anticipating that we'll be meeting in person starting on February 1st, but we're still waiting from the administration to confirm all of that. So be on the lookout for any messages over the next day or 2 or 3, or at least by Monday at the absolute latest. Again, I'm hoping to be seeing y'all in person soon, but we'll find out. So take care, have a good one. We'll see you Thursday.